Hello and welcome back to Physical Geology. I am Robert Lopez. Today I want to go over the Google Earth worksheets and exercises that we'll do through Canvas. So let's go here to the modules, and here we'll start with the first one, which is Chapter 1, and we'll look at Geotour's Earth and Sky. So when we click on this, we'll go to the quiz, and then this quiz will be linked to the Google Earth exercises that I'll show you here in a moment. So let's open this up. And this one has 18 questions, right? There's 18 questions here you'll see on the sidebar here. And the first question deals with the Eagle Nebula. And when we go to Google Earth, I'll show you this in a moment, we want to select the sky database here so we can look out into the constellations. All right, so here we are in Google Earth. And note that I've downloaded the Geotours 2E file already. And so this is what we want to use, but don't activate any of these yet, because if you activate anything here, it's going to populate it with maps and charts and earthquakes and volcanoes, features that really clutter up what we want to see. Another thing about Google Earth is that the files usually go in this places folder, whereas the layers like cities, borders, buildings, that'll be this box down in here. So you can see some of the layers I have turned on, in this case, the borders for countries, right? Now for our Geotours 2E file, right, we don't want to activate anything yet. We want to look at this section 2, because section 2 contains all the Geotours exercises. For example, here is Geotour A, there's B. So remember, we're going to do maybe about 6 or 7 of these here. So we're doing Earth and Sky. So let's expand Earth and Sky. And Earth and Sky has the 18 problems. So you can see there is the 18 problems right here as well. And so we'll look at the first problem, right? So, but before we do that, remember that it wants us to look at the Google Sky up here. So we'll click on this image of Saturn here and go to Sky. And then let's activate Earth and Sky here. So we'll click this button here. And then we want to go to problem 1. So let's double click on problem 1 over here in the Places panel. And that should take us to the Eagle Nebula, which is a stellar nursery where there are stars actually being born, right? There's gases coming together forming these stars. And so here is the Eagle Nebula. This is our problem 1. And so if we read the question here, it's asking us about how far across this is in terms of a light. So the leftmost pillar is a current length of 4 light years. So the leftmost pillar has a length of 4 light years going from bottom to top, and 1 light year is 9.5 trillion years. So what is the length of a pillar in kilometers? So basically all they're asking us to do, in this case, is a math problem. So what we do, we have the 4 light years, and we're multiplying those by 9.5 trillion kilometers, so we get 38 trillion kilometers. So that's actually a pretty easy one right there. For question 2, let's look at this main sequence star, Tau Theta, and let's see what's going on with this one here. So let's click on it, double click on problem 2 here. It's going to take us to this main sequence stars, which is kind of similar to Earth, right? So there's a star, and then what are the questions they're asking us here? So hydrogen fusion, they're talking about nuclear fusion here, main sequence stars. Both our sun and this star, Tau Theta, are currently at this stage where they're using hydrogen as a nuclear fuel for nuclear fusion, right? And so both are considered yellow dwarf stars. For most stars, the main sequence stage lasts the longest. In the case for our star, it's about 10 billion years. We're about halfway through the life cycle of this star here. So which type of star will have the longer main sequence stage and therefore live the longest, right? So remember, intermediate to low mass stars like ours are using their fuel more conservatively, and so they're not burning through it. Whereas these high mass stars, the blue giant stars, the white hot, blue hot stars, they're going through their hydrogen fuel very rapidly. At a short history, 1-2 billion years at the most, they're going to go to supernova. They're just going to explode. They're burning too fast. So the answer here would be these lower mass stars. So question 3 is looking at a red giant, Aldebaran. And so let's take a look at Aldebaran. So we'll go to problem 3 here in Google Earth. And there it is right there. That's a red giant there. And then, so eventually the majority of hydrogen in the core of the main sequence stars is consumed, and the core begins to collapse due to gravity. Very low mass stars form white dwarf, whereas most other stars collapse and heat up until helium fuses. This fusion causes stars to expand outward several times larger than before, forming a red giant. Aldebaran is an example of this. When this happens to our sun in about 4 to 5 billion years, what will happen to Earth? So in this case, Earth will lose its atmosphere, water, and may or may not be completely vaporized. That's because as our star will, we're really going to it probably is going to turn into a red giant star. In fact, here in chapter 19 on page 627, it discusses how if the Earth were larger, you would see perhaps a supernova explosion, but stars our size would really turn into a red giant, right? And so if we take a look at the Earth would lose its atmosphere, right? Because and it may or may not expand to the orbit of Earth here. So let's look at the questions here. And so Earth will lose its atmosphere and water and may or may not be consumed or completely vaporized, depending on how large this the red giant becomes. So I'll let you go through questions 4, 5, and 6 on your own because they're pretty straightforward. I want to go over to question 7, 8, and some of the other ones here because they deal with something a little bit different. All right, so now we're going to look at the moon here. And in the moon, we're going to see where the Apollo missions landed, Apollo 11 and Apollo 16. So which of this region contains impact features that are larger in size? So these are where meteors hit and have a higher concentration density. So let's take a look at these two sites, Sea Tranquility and the Descartes Lunar Highlands. So let's go to the moon. Apollo 11 in Mare Tranquillities and Apollo 16. So let's see. So this is Apollo 16 right here. And so these are the highlands. And if we go to this one here, Apollo 11 landed over here in the Sea of Tranquility. So one thing I noticed right away is that there are some impacts in here. But if we go down here to where Apollo 16 landed, you can see there are far more impacts, right? So for this one, which region contains impact features that are larger in size and that have a higher concentration density? That would be the Descartes Lunar Highlands there, right? Now again, looking at impact features of the moon, based on your answers to question 8, which rock unit on the surface of the moon is the youngest? Before we can do question 9, we need to turn on some features for the moon. So here under layers, we want to go to Moon Gallery, Apollo missions 11 and 16, and then we want to show the historic geologic charts, right? So that's actually down here. So when we look at the Moon Gallery, Apollo missions, we want to show we'll turn on the historic charts here, maps, and so it's going to give us these geologic maps of the moon. And so let's go back to these questions. So there's question 9A and 9B, right? So 9A is showing us where Apollo 11 landed, right over here. So it's mostly pink here. And remember, that's the younger region there. And then for 9B, which are the highlands where Apollo 16 landed, here you can see there's some more purples and grays and blues. So the question here is asking us, based on your answers to question 8, which rock unit on the surface of the moon is the youngest? So that would be the pink, where the Sea and Tranquility is, right? And which of the following best describes the nature of the dark Madhya? So that's so the Madhya are the dark regions there. So let's look at question 10 here, the lunar maps. Probably the best thing to do here is probably turn off our historic map data here because it's kind of cluttering. So that's the question. This is the near side of the moon. That's the side we say. So the Madhya are these dark areas, primarily where basalt flows are, right? And the highlands are these older regions over here. And the far side of the moon, we can see that it's mostly highlands over here. There are fewer madia. There's one right in here. So the near side of the moon seems to have more of these madia, right, which are basalt flows. So the question here for number 10, which of the following best describes the nature of the dark madia? So which of the following best describes the nature of the dark madia? There is no difference. No, there is definitely a difference. The near side has more madia, so definitely. And it may be due to more of this or just larger volcanic flows on the near side of the moon.